We're going to talk briefly about what continuity is, and then also how to determine whether or not a function is continuous. Continuity is whether or not a function is continuous, and we're usually looking at a specific x value. Now, many of the functions that you've worked with are nice, well-behaved functions that are always continuous. So for example, linear functions, quadratic functions, I could say in general, all polynomial functions are continuous because they're nice, well-behaved graphs that have no holes, no gaps, no asymptotes. So continuous functions are easy to work with, but oftentimes we're going to work with piecewise functions, which may or may not have places where they are discontinuous. So I've already stated kind of the general definition of continuity: no holes, no gaps, no asymptotes. This is our formal definition of continuity. So in order for a function to be continuous at a particular x value, which we will call c, three things have to happen. Number one, the function value has to exist. What that means is that on the function, there is a solid point somewhere at that x value. So there's not just holes. Number two, the limit has to exist. That means as we approach that particular x value from both sides, it is approaching the same y value. And finally, the function value and the limit have to be the same thing. Here are some visual examples of each part of the definition failing. So in my first example here, this is an example of the function value not existing. So if you look at our x value in question, c, if we go up to the function, there's a hole there. Therefore, the function value does not exist. Therefore, this function would not be continuous at the x value of c. In number two, this is failing the second part of the definition. If you notice, as we approach c from the left and from the right, we would be predicting different y values. Therefore, this function is not continuous at the x value of c. Finally, in number three, this is an example of the function having a limit at c and having a function value, but since they are not the same thing, the function is not continuous. So you would predict a particular y value for the limit, but that function value is a different y value. Therefore, it is not continuous. So here is an example of a piecewise function, and let's say we want to determine whether or not this function is continuous at the x value in question. Now, one thing that I notice right away is since I have a linear function and I have a quadratic function, these functions are by nature continuous. They have no holes, no gaps, or asymptotes. So the place that we may have an issue is where the two different functions come together, which in this case is the x value of 3. So in order to determine whether or not this piecewise function is continuous, I need to see if they're going to meet at the same y value. The way that I can do that algebraically, I'm going to call this one f1. I can evaluate the first function at 3, which would give me 2 times 3 minus 1. That's 6 minus 1, or 5. My second part of the function, I have 3 squared minus 4. That's 9 minus 4, which is 5. So what this is telling me is my two functions meet at the same place, therefore they are continuous. You can also always use a graphical approach to check for continuity. If you notice, I've graphed the first branch of the function in green, y equals 2x minus 1. And so that function exists from 3 to negative infinity. Notice that because this does not have an equal to, I have an open circle here. Now, that circle has been closed by the second branch of the function because I do have the equal to right here. And so I've graphed that in red. So this is showing that the two different branches of function do indeed meet at a x value of 3 and a y value of 5. Here's another example of determining continuity of a piecewise function. So again, I've got a piecewise function with two branches. The first one, y is equal to 3x squared. The second one, y equals 2x minus 1. Notice these are both polynomials, they're well-behaved functions, so the only place that I'm questioning the continuity is where the two come together at -1. So I'll evaluate each function, so I'll call this f of 1, do 3 times -1 squared. Careful to remember here that -1 squared is +1, so that gives me +3. And f of 2 at -1 would be 2 times -1 minus 1, which is -3. Now, I purposely did this as a reminder. Be careful when you're squaring that negative, that it's positive. Also, if you're typing it into your calculator, make sure you put the parentheses around that negative number so it gives you an accurate value. Therefore, since these two are different, this function is not continuous at x equals -1.